Hi, my name is Sarah Harris, and I will be presenting with my co-author, Danny Chaver Martinez, about RVfpga, two courses that teach how to use a RISC-V system on chip SoC targeted to an FPGA in computer architecture education. So we've designed these two courses to help people understand how to use and not only use, but also modify a RISC-V core and system on chip. So the first course, called RVfpga, shows how to use and then extend the RISC-V SoC to add instructions, to add peripherals, and also the basics of programming the RISC-V core. The second course, RVfpga SoC, shows how to build a RISC-V SoC from building blocks, from the processor and interfaces and peripherals. And after completing these courses, you'll walk away with a working RISC-V processor, understand the tool chain, how to use the basically the RISC-V ecosystem, and also understand how to modify the core and the SoC. The course is available freely from Imagination Technologies upon registration at the link below. Our materials use the Swerve EH1 core, a commercial core from Western Digital, and Swerve ULF SoC. We actually used an extended version of that, thus the X here, Swerve ULF X. We add a few, some peripherals here, and then show how to extend it even further in the labs. Here's the hierarchy of the RVfpga system. Again, the Swerve core here in the center, building up to the SoC, and then targeting it to the Nexus A7 FPGA board or simulation. And here's a picture on the right of the Nexus A7 FPGA board. The software required is all free, and shown here. And the hardware is available as part of the download from Imagination Technologies, all except for the FPGA board, which is optional, that costs $199 for academics or $265 for the commercial price.
The RVfpga course contains 20 labs. Lab 1 shows how to use Silence Vivado to target the RVfpga system to the Nexus A7 board. Labs 2 through 5 show how to write C and RISC-V assembly programs and run them in simulation and in hardware. Labs 6 through 10 show how to use the peripherals available in the RVfpga system and also how to modify it to add new peripherals. Lab 11 provides a detailed introduction to the Swerve EH1 microarchitecture and shows how to configure the processor and how to use the performance counters and real benchmarks to test the system. Labs 12 and 13 investigate arithmetic logic instructions and also memory instructions. Labs 14, 15, and 16 investigate structural, data, and control hazards, branch instructions, and the G-share branch predictor. Lab 17 analyzes two-way superscalar execution. Lab 18 shows how to add new instructions to the core as well as new hardware counters. Finally, Labs 19 and 20 show how to use the instruction cache and the ICCM and DCCM. We next show a demo of one of the multiple exercises that we propose in our labs. We first program the FPGA with the RVfpga system using VS Code and Platform I/O. Once the board has been programmed, we run the program on the RVfpga system. This exercise from Lab 10 asks the students to create a program in C that receives a character from the keyboard and displays it using the UART module. You can see that every time that we press a key, the key is shown both on the serial terminal and on the 7-segment displays. The RVfpga SoC course includes 5 labs. Labs 1 and 2 show how to use the Vivado block design tool to create the RVfpga SoC from scratch, and also how to run programs on it, either in simulation or in hardware. Lab 3 shows a second approach for building the RVfpga system using FuseSock. Lab 4 shows how to build, run, and use Chaver on the RVfpga system. And finally, Lab 5 shows how to build a TensorFlow lead project for Chaver and run it on the SoC.
In conclusion, RVfpga is a sequence of 2 courses that show how to use a commercial RISC-V core and its toolchain, and not only how to understand and use this core, but also how to extend it and to extend the SoC. And RVfpga SoC shows how to build a RISC-V SoC from scratch, from building blocks including the processor core, the peripherals, and the interfaces. These materials are freely available from Imagination Technologies, and they're available in several languages: English, Chinese, both simplified and traditional, Spanish, Japanese, Korean, and Turkish. And these materials are available in their, the sources of them, including Word documents for the instructions in the labs. And we plan on developing the following additional resources to accompany these courses, including hands-on workshops, a self-guided MOOC, and materials that show how to target smaller FPGA boards. And in addition, the material is supported by an accompanying textbook, Digital Design and Computer Architecture, RISC-V edition by Harris and Harris, that will be published in September 2021.
Thank you for listening. We'll now try to answer any questions that you may have.